random analog of continuous time dynamic programs. Okay, so just as the random analog of a dynamic program is a Markov decision process, then we want to consider the analog of a continuous time dynamic program as a diffusion control problem. Okay, and just as we were able to derive a continuous dynamic program as a kind of Taylor, as the limit we get from a Taylor approximation to a discrete time dynamic program, we want to do the same with a diffusion control problem. We want to essentially look at a Markov decision process as an approximation of a diffusion control problem and look how we can derive things like the Hamilton-Jacobi-Bellman equation from the Bellman equation for the Markov decision process. Okay, so anyway, what I'll first do is go about defining what we mean by a diffusion control problem. Okay, and then we'll focus on this kind of heuristic derivation, and then we'll give a kind of rigorous result which says that if we can solve the HJB equation, Hamilton-Jacobi-Bellman equation, which is the analog of the Bellman equation for this control problem, then we have actually an optimal solution to the problem. Okay? All right. So this is going to be useful later on because we're going to consider controlling different sorts of diffusion processes which are going to correspond to things like stock prices. And the kind of things we want to control is in order to solve optimizations, we want to say maximize our reward from consumption or maximize our utility. Okay? All right. So what do we mean by a diffusion control problem? Okay. So here we're going to consider the continuous time analog of a Markov decision process. Okay, so it's not the only continuous time analog, but certainly the one that's most relevant when we're considering things driven by a Brownian motion. Okay. All right. So time again is going to be continuous. Okay, so it's going to be a positive real number, and the state of the system, x of t, belong to some set of states belong to r to the n. Okay, and we're going to have actions. Okay, which we can allow to be a little bit more abstract if we want, that belong to some set script A. Okay, now we're going to consider again a plant equation and then a optimization problem that we want to solve subject to satisfying the conditions of that plant equation. Okay, so the plant equation that determines the evolution of the state x of t is going to be given by two functions, our kind of drift function, mu of t, x of t, a of t. Okay, and a diffusion term, sigma t, x of t, a of t. I'm going to assume that the state evolves according to a stochastic differential equation, which is given by dx of t, so the change in x of t, is given by some drift, which is a function of time, the state, and the action that you choose, okay, and some volatility due to this stochastic integral where we say that we've got sort of a volatility, sigma of t, x of t, a of t, and then we integrate that with respect to Brownian motion to give some noise. Okay, so here b of t is assumed to be an m-dimensional Brownian motion. Okay, so this is the plant equation in the case of a diffusion control problem, right? So the real difference from a normal stochastic differential equation, as you've seen so far, is that we're adding these additional terms where we control or have some choice of what the drift and diffusivity of our process are. Okay? So a policy, pi, chooses an action, pi of t, each time t. And there are various conditions that we could add on to this if you're familiar with the different ideas in stochastic integration. In particular, we could say that pi of t is adapted and previsible. Okay? So it's something where up till time t, we only use sort of the information up to, but not necessarily including the state at time t. Okay? Okay, and we're going to let P be the set of policies. Okay? All right, so that's basically the sets of actions that we can take as a continuous, as time evolves. Okay? There are various additional sorts of assumptions that we might want to consider on that to make everything nice and well posed and all the rest of it, but we're not going to go into the kind of dotting I's and crossing T's theory of this. Okay? Okay. Now, as time evolves, there's going to be instantaneous cost for taking an action A in state x at time t. We're going to let C of t of a of x be the cost at time t for taking action A when in state x. Okay, and then there's going to be a termination cost, C capital T of x, okay, which is a cost incurred at the final time at time capital T. Okay, now from this we can define a diffusion control problem. Okay, so it's very similar to before when we had our continuous time dynamic programs. Okay, we want to minimize over the sets of policies, okay, the integral of the costs. Okay, so that's the same as before, and we're going to discount, due to say interest rates and all the rest of it, we're going to discount the costs over time. All right, then so we integrate that with respect to time, and then we have the final termination cost here. All right, now the only difference is that we now have a random process, and so we want to average over the sets of things that can happen. Okay, so if we're at state x0, we take the expectation of this over the paths of the stochastic integral given the choices that we're making according to the policy. Okay, and then we're further going to define, a little bit like before, we're going to let C of tau of x of pi and respectively L of tau of pi correspond to the optimal solution be the objective that we reach from this diffusion control problem, but where the integral, rather than started at time 0, is started at some different time tau. Okay, and at time tau we let this be equal to x. Slight typo, that should be tau. Okay, all right. So essentially we're looking to minimize minimize the expected costs over the different paths of the stochastic integral. Okay, and again we're going to have the analogue of the Bellman equation for this type of problem. Okay, so specifically the Hamilton-Jacobi-Bellman equation for a diffusion control problem is the following. Okay, we look to minimize the instantaneous costs, okay, of some terms that involve the partial derivatives. Okay, now we've got a partial derivative with respect to time, then a partial derivative with respect to space, then now, which wasn't present before due to the diffusivity of the process, we've got a partial derivative, a second order partial derivative of this L of t function, and then we minus off a term that accounts for the discount. Okay, now where does this come from? You can notice, okay, that if I was to look at the process L of t of x of t, okay, and I was to try to derive the Ito's formula for that, okay, so we've got a function of x of t and t. I could expand this and apply Ito's formula and look at the drift that occurred when I applied Ito's formula. And you can notice that this term here is a drift that we get from Ito for dl of t x of t. Okay, so that's an important point to notice, that essentially we're looking to minimize the cost, and then when we're looking into the future and looking at the effect beyond the instantaneous cost, we're essentially looking at the drift term of this part from applying Ito's formula. Okay, now this is called the Hamilton-Jacobi-Bellman equation, and it's a continuous analogue of the Bellman equation for a Markov decision process. Okay, so now what I'm going to kind of concentrate on doing is explaining again, in similar terms to the way we did for a continuous time dynamic program, why this HJB equation makes sense. Okay, so why, given that you understand the theory of Markov decision processes, why is this HJB equation the right equation to look at? Okay, so why do we have this minimization equal to 0? Okay, so let's go through that. So we're going to heuristically develop a Bellman equation for stochastic differential equations using our knowledge of the Bellman equation for Markov decision processes. Okay, so let's go through that. Okay. Oops. Sorry, just be a second. Just need to get something up here. Okay, here we go. All right. So the first thing, I'm going to do heuristic derivation of the HJB equation. We suppose, for simplicity, that xt belongs to R. So we're not going to let it belong to R to the n. We're just going to go with a kind of one-dimensional diffusion here. Okay. So argue that the Planck equation that we gave above is approximated by the following. Okay. Well, so in other words, that the change in x is given by the drift plus sigma t x of t pi of t, and then that's altered by the perturbation that we get from a Brownian motion, okay, between time, and a slight typo here again, between time little t plus delta to b of t, okay? Well, so the answer to this, is that it's exactly the same as our previous exercise. Specifically, let me get the number up. So went from our heuristic analysis of stochastic differential equations. Okay, so let me just get that. So when we were looking at stochastic differential equations just before stochastic integration, note that we had this exercise here, exercise 77. Okay, so what we're looking at now is essentially the same thing. This is essentially the same argument. Oops. As exercise 77. Okay. Next, argue that for delta, small and positive, the cost function that we considered before is approximated by the following. So the cost here, which was an integral, okay, can be replaced by this summation. Okay. Well, we can. So notice that we've replaced the integral, okay, from 0 to t, e to the minus alpha t, c of t of x of t of pi of t dt plus e to the minus alpha t, capital C of t, x of t by the following, by this. Okay, we've actually seen that before. We didn't have the expectation in it, so we replace the expectation of this. Well, we replace this integral with this summation here. Okay, and let's just ignore the expectation for now. We've actually seen that already. This is what we did. We did exactly the same trick when we considered the discrete time analog of a continuous time diffusion. Okay, so let's just look at that. So that was over here when we're looking at continuous time control. Okay, so these are the notes on continuous time dynamic programming. We note that here we noticed that heuristically we could form a good approximation of our cost function by replacing it with exactly this sum. Okay, so it's exactly the same approximation that we're using there. It's from exercise 65. All right. This follows from exercise 65. Okay, so it's exactly the same argument that we saw previously. Okay, so now argue that L of t of x of t the optimal value function approximately satisfies the following expression. Okay, well, here we've got a optimal objective for an MDP. Okay, and here we've got a plant equation for an MDP. Okay, so we could write down the Bellman equation for that. There's an instantaneous cost here, all right, and an evolution that gives you the next state given the current state. Okay, so we'll see that the optimal value function here is, as given by the Bellman equation, the minimum over the instantaneous costs plus the expected value, given the current state and the action that you choose, of the value function, the optimal value function, at the next time and the next state. Okay? And because we're discounting time by a factor of 1 minus alpha to the delta, we apply a discount factor. Okay? So in other words, the answer to this is that, note, this is the Bellman equation for the Markov decision process given by plant equation in exercise 83 and the value function and the objective given in 84. Okay? All right. So now we see that we essentially have this Bellman equation with some deltas in. Okay? So that gives a good approximation. As delta gets smaller and smaller, it should give us a better and better approximation to what the optimality condition should be for this diffusion control problem. Okay? So now, notice that we've got one term in here, L of t plus delta, x of t plus delta. All right? That's somehow the most complicated term in this expression. We want to kind of deal with it. Okay, so this is how we're going to do it. Okay, we're going to look at the change in x of t plus delta, sorry, L of t plus delta, x of t plus delta, okay? And it says to argue that this can be approximated by this, okay? Well, this is exactly Ito's formula for this function. This approximation is exactly Ito's formula okay, for L of t of x of t. Okay, so we can either derive that via a Taylor expansion in the same way that we did before, or we could quote Ito's formula. Okay, so let's exactly pick up where we got that from. So if we go back to the stochastic integration notes here, okay, so these are the stochastic integration recap notes. Notice this is exactly this approximation. If we want to do it by looking at a Taylor expansion, is exactly 78. Or if we want to directly quote Ito's formula, okay, this is actually the one-dimensional version, but it doesn't matter. We can either quote exercise 79 or 78. Okay, we're applying exactly the same idea and approximation here. Okay, so this approximation is exactly Ito's formula for L of t of x of t as given in exercise 78, for example. Okay, so you can go through the steps exactly as before, do that Taylor expansion, and you'll arrive at this approximation. All right. Okay, so now rather than having this L of t plus delta, x of t plus delta, okay, that we have here, and notice I could minus off this L of t of x of t from this term, so I can look at the difference between this term and this term. I can replace it, so I can replace it with this, right? Right, and the thing to look out for is actually the thing in the square brackets here, because notice we're going to take an expectation on this, and the expectation of this term is going to be 0. Okay, so that's what we'll see next. Okay, so then it says, argue that L of t of x satisfies the following equation, i.e. this is exactly the HJB equation that I wrote down earlier for a one-dimensional stochastic differential equation. Okay, so let's do that. So, answer. So, E of L of t of x of t plus delta minus L of t of x of t, okay, is equal to the expected value of the term that I wrote up above. Okay, so I'll just zoom out a little bit so we can grab it here. So delta, partial derivative, sorry, it's not a delta, the partial derivative with respect to time of L, okay, where L means L of t of x of t, plus mu, where mu here means mu of t x of t times pi, dot the partial derivative with respect to x of L, plus sigma squared, I'm scrapping a bunch of these terms here, divided by 2, and then second order derivatives of L, okay, and then all of that's going to be times by delta. And why haven't I included this term? Because, well, the expected value of this term is 0. Okay? And notice now we've got something that's deterministic. Okay? At least up until time t, given time t, this is a deterministic function. All right? So given I take x and x at a, then this is determined completely. It's no longer random. We've got with everything here times by delta. Okay, so what am I going to end up putting in this expression over here? Well, I'm going to have c of t x of a times delta, and then I'm going to have one lot of x of L of t plus delta x of t plus 1 minus L of x minus alpha delta lots of this expression. So let me just write that down. So from exercise 85, okay, let's get everything together here. We have that, 0 equals the minimum over the sets of actions of c of t, x of t, a, times delta, plus e, x of a, L of t plus delta, x of t plus delta, minus L of t, x of t, okay, minus alpha delta e x of a, L of t plus delta, x of t plus delta. Okay, so why is that? So notice I have taken the expression from 85, I've moved the L of t over to this side, and I've grabbed the alpha delta term out. Okay? All right. So now, and I've said that this expectation here is going to be given by delta times the term in the square brackets. Okay, so I'm going to have min C of t, and I'm going to grab the delta out at the front here. This delta is going to go out to the front. C of t, this guy, plus the term in the square brackets here, partial derivative of L, plus mu of t of x of a, this guy here, dotted with the partial derivative with respect to x, then added on sigma squared divided by 2, and then the second order partial derivative of this guy, okay, and the delta I've absorbed out of the front. And then what I'm left with is minus alpha e of x of a of L of t plus delta x of t plus delta. Okay, and now we can imagine with this term that as I let delta go to 0, this is going to converge to the state at time t, which we've assumed to be x, and this is going to converge to t, so we can imagine this is just, all of this is going to converge just to the value of L, okay, or L of x of a, okay, oh, sorry, L of x, okay, so as delta goes to 0, okay, so first of all, cancelling this guy out and letting delta go to 0, we're going to arrive at the equation 0 equals the minimum over the sets of actions c of t of x of a plus partial derivative of L of x of t plus x of t of x of a dotted with the partial derivative of L plus sigma squared over 2 of x at time t of x of a, second order partial derivative of that guy with respect to x, then minus alpha lots of this guy evaluated when delta equals 0, which is going to give me L of t of x. Okay, in other words, I get exactly this. Okay, so essentially it's exactly the same idea as the HJB equation for continuous time control problems held. We essentially do a Taylor expansion idea, and things are a little bit complicated because we can't apply chain rule, we have to use Ito's formula, so that just makes the derivation sort of around this point a little bit more cumbersome, but it's still the same basic idea. So it combines that approximation we did for continuous time diffusion control problems, and it applies those stochastic integration kind of heuristic ideas. Okay, but from all of that we see that this HJB equation seems to be exactly what we get when we look at the conditions of the Bellman equation for the discrete time analog of this diffusion control problem. Okay, all right, so that's all well and good. So that's probably how back of the envelope style you derive what the HJB equation is and why you'd think it's the right thing. Okay, that doesn't mean it necessarily is the right thing. I'd say it's good enough for, you know, at least sort of for more applied people, for, you know, for why this is true. It's certainly enough to satisfy me for the better part. Still, we really ideally want to have a rigorous proof that this is the correct thing. Okay, so one way of proving, okay, that the HJB equation that we wrote down earlier is the correct thing is we can use the following condition. Okay, this gives a nice way of deriving optimality conditions. Okay, so it's one of the ways we can go about deriving the optimality of a specific policy. Okay, so let's go about doing this. This is called the Davis-Varaiya Martingale principle of optimality. Okay, so let's suppose that we can find a function L of t of x that satisfies at time t our termination condition, and such that for any policy pi with states x of t, that the following function m of t, which is equal to L of t x of t plus this integral, there's a slight typo here, we shouldn't have this bar here, but anyway, so ignore that. M of t plus the integral from 0 to t e to the minus alpha tau, and then the instantaneous cost at time tau d tau, provided that is a sub-Martingale, and moreover if we can find some policy pi star for which M of t is a martingale, so when I change this policy here to this special policy pi star, it becomes a martingale, then you can say that policy is optimal, and the optimal value function is given by the value of this function at time 0. Alright, so basically if we can find a function that we can make sub-martingales out of this, and we can find a specific policy that makes it a martingale, then we've satisfied optimality. Okay, so this is it's kind of the analogue of that integral. We had this kind of derivative type argument before we considered the continuous time dynamic programming setting, and this is kind of the random equivalent, and obviously we're not going for integrals, derivatives and trying to get them going in the right direction, going up or down, but we're going to be looking at martingales. Okay? All right. Okay. Right. So sub-martingale means basically a M of t in expectation goes up. Okay? So since M of t is a sub-martingale, so mg here I use to mean martingale, so sub-martingale, for a policy pi, we have that m of 0 is less than the value of the martingale at time, the final time m of t. Okay? And by definition, this integral is 0 at time t equals 0, so we're just left with L of 0 of x of 0 here. Okay? However, at time t, we've said that it's equal to the termination cost plus the integral of this guy, integral from 0 to t, capital T, sorry, e to the minus alpha of t, oh, sorry, of tau, because we're integrating tau, c of tau, x of tau, pi, d tau, okay, which is exactly the cost function for policy tau. Okay, so this is exactly the cost starting from x0 following a policy pi. Okay, so we know that this L of 0 of x of 0 is less than the cost function for any policy. Okay, however, if m of t is a martingale, so proper martingale, for pi star, then all of this argument follows, but with this being an equality. So then L of 0 of x of 0 is equal to the cost, sorry, this should be in curly brackets, x really, and it should be here as well, to be honest, is equal to the cost starting from state x0 and following the policy pi. In other words, the cost following pi star is less than the cost of any policy. In other words, the cost of that policy is less than everything, so it's an optimal policy. Okay, so that then gives us a way of checking whether a policy is optimal or not. Okay, so wrapped up in this statement, we'll notice this sub-Martingale condition is essentially corresponding to whether that drift term in the minimization is positive or not. Okay, so wrapped up in this expression, a bit like we used before, actually what we're saying is if this term is positive, then the drift of this martingale is going to be going up. So we're going to have a the drift of this empty term is going to be going up, so we're going to have a sub-martingale. Well, if we minimize this and it's equal to 0, then the drift of this function, m of t, is 0. In other words, we're going to get a martingale. and thus get an optimal policy. Okay, so that's the connection between this Davis-Varaiya Martingale principle of optimality and that HJB equation that we wrote down before. Okay, so it's two sort of equivalent ways of looking at optimality for these types of problems. Okay, so next time we're going to start to look at actually a specific application of these, and obviously it's one that's very relevant to financial control. We're going to look at portfolio optimization in the style of Merton. So you've covered the kind of Black-Scholes framework, of which Merton was a key contributor, and the three of them were essentially awarded Nobel Prizes, Merton, Black and Scholes, for their work on this theory. And so Merton developed a theory that looked into optimal investment of capital using these kind of diffusion control problem frameworks. Okay, so that's the next thing we'll look into. We'll look into how that theory applies to when you want to kind of optimize your investments in order to maximize, say, your consumption or utility in a system. Okay, so that's the next thing that's going to be coming up. Okay, all right, thanks.